Imagine a magnetic field created by a magnetic north pole of strength m1. This will create a magnetic field in the region around it. Now let us place a magnetic south pole in this field. We observe that the magnetic force experienced by the south pole increases as we decrease the distance between these two poles. We also observe that as we increase the magnitude of pole strengths of any of the poles, the magnetic force between them increases. It has been found that the magnetic force between two magnetic fields is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. This is called the inverse square law of magnetism. It states that the magnetic force between two magnetic fields is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. We will now express this law mathematically. Consider two bar magnets of pole strengths m1 and m2. These poles are separated by a distance r. The force of attraction F or repulsion between them depends on 1. Their pole strengths m1 and m2, 2. Distance of separation r, and 3. The medium in which they exist. Therefore, mathematically we can write this as F is directly proportional to m1, m2, and F is indirectly proportional to 1 by r square, or F is equal to k m1 m2 divided by r square, where k is the constant of proportionality and it depends on the magnetic properties of the surrounding medium. The value of k also depends upon the system of units used for pole strength m.
The magnetic property of the medium is represented by K in this equation and is called magnetic permeability and is denoted by mu. This property indicates the influence of the medium over the magnetic field set up by a magnet. It is defined as the ability of the medium to allow magnetic lines of force to pass through it.
Depending on the value of mu, the magnetic force acting between the poles change. The value of k in this equation depends on the system of units used for the magnetic moment m. In MK's system of units, Weber, that is Wb, is the unit of magnetic pole strength. In SI system, the pole strength is measured in units of ampere meter, that is Am. Thus, in SI system, the form of inverse square law in free space is given by F is equal to mu0 divided by 4 pi m1 m2 divided by r square. This is 2, where mu0 is equal to 4 pi multiplied by 10 to the power minus 7 Henry per meter, which is treated as a universal constant. From this, the units of pole strength in MK's system and SI system have the relation 1 Weber is equal to mu0 Am. Instead of free space, if any other medium exists, the inverse square law in equation 2 takes the form F dash is equal to mu divided by 4 pi m1 m2 divided by r square, that is equation 3, where mu is the absolute magnetic permeability of the medium. Note that in this equation F dash is different because the medium is different. Dividing equation 3 by 2, we have F dash divided by F, which is equal to mu divided by mu0, which is equation 4. This ratio of the magnetic force in a medium to the magnetic force in free space is defined as relative permeability mu r. Hence, mu r is equal to mu divided by mu0, which is equation 5, or mu is equal to mu r multiplied by mu0. Note that the relative permeability is a ratio of mu and mu0 and hence has no units. For air or vacuum, mu r is equal to 1. Using the value of mu0 in the equation of inverse square law of attraction of repulsion, we have F is equal to 10 to the power minus 7 multiplied by m1 m2 divided by r square, which is equation number 7. From this formula, we define unit magnetic pole strength. If m1 is equal to m2 is equal to 1, am r is equal to 1 meter, then F is equal to 10 to the power minus 7 newtons. The unit magnetic pole is defined as that pole which repels an identical pole at 1 meter distance with a force of 10 to the power minus 7 newtons.
Let us move on to understanding what magnetic field induction is. You have already seen that when a magnet is placed in a medium, magnetic force is experienced by magnetic substances placed in that medium. Magnetic field is defined as a region around a magnet in which magnetic force is detected. It is easy to imagine this field as made up of magnetic lines of force. The total number of magnetic lines of force in a given area is called magnetic flux, phi. This is measured in units of Weber, Wb. Magnetic flux density or magnetic field induction B is defined as the magnetic flux passing through a unit normal area. If A is the area through which a flux phi expressed in Webers passes normally, B is given by B is equals to phi by A. The magnetic flux density at any point can be shown to be equal to the force acting on a unit north pole. By convention, the magnetic induction B due to a magnet at a point in a medium is defined with respect to a unit north pole. It is measured using the inverse square law. For a unit north pole, m1 is equals to 1 ampere meter. Then, from the equation of inverse square law of force of attraction, if m2 is equal to m, the pole strength of any magnet we have, F is equals to mu naught by 4 pi into m by r square.
The magnetic field induction B due to a magnet at a point in a medium is defined as the force acting on a unit north pole placed at that point. From the equation of pole strength of a magnet for free space, B is equal to mu0 divided by 4 pi m divided by r square, which is equation number 10. If now a north pole of a strength m is placed at a point where the magnetic induction is B, the force acting on it is given by F is equal to mb, or B is equal to F divided by m. Thus, the units of B are Newton by ampere meter. From the equation of magnetic field induction, since pi is measured in Webers, the units of B are also given as Wb per meter square, called Tesla. 1 Tesla is equal to 10 to the power 4 Gauss, where Gauss is a CGS unit of intensity of magnetic field. The strength of a magnetic field at a point in CGS units is defined by the term intensity of magnetic field or magnetic field strength H. In CGS units of magnetic field, the equation for free space by inverse square law is given by F is equal to K into m1 m2 divided by r square, which is equation number 11. Where K is equal to 1 divided by mu. Mu is the permeability of free space, which is equal to 1 in CGS system. In equation 11, if m1 is equal to unit north pole, m2 is equal to m, then the force acting is called H. Thus, H is equal to m divided by r square. The intensity of magnetic field H at a point is defined as the force acting on a unit north pole placed at that point, independent of the medium.
The units of H in CGS system are Gauss. Thus, conceptually, both H and B are the same. Both H and B represent a magnetic field at a point. But there are certain important differences that we will now look into. In SI system of units, consistency among the units of different physical quantities is brought about by introducing suitable constants. In SI system, H is given by H is equals to m by 4 pi r square. The units of H in SI system are ampere by meter. Here, H is used without considering the role of medium or even free space. Thus, the relation between B and H is given by B is equals to mu naught into H. Note that B and H are essentially the same in a vacuum, but B is macroscopic magnetic field inside the matter, while H is the field inside the medium. Both B and H give the strength of the magnetic field at a point. However, numerically, B and H differ by a constant mu naught in free space, so that mu naught is equals to B by H, or B is equals to mu naught into H. The quantity H can be treated as a magnetic field or a magnetizing force or magnetizing field produced in a medium by some external agent. If SI system is adopted, the magnetizing field is also written as B naught is equals to mu naught into H. But within the medium, the field experienced will be B differing by a constant, which is the property of the medium called absolute permeability mu. Thus, B is equals to mu into H. Since mu is equals to mu naught into mu r, we also have B is equals to mu naught into mu r. H is equals to mu r into B naught. Here, H or B naught is the applied field. B is the field experienced by the substance. The difference comes because of induction effects of the medium. Here, B corresponds to B naught.
For example, if the medium is a soft iron, mu r value is far greater than 1, and hence the effective field inside it will be B much more than the applied field H or B0. In practice, we use only SI units for all the magnetic quantities. However, in some laboratories, still the CGS unit Gauss is being used for magnetic field H.
Let us now summarize what we have learnt so far. The ability of a pole of a magnet to attract or repel another magnetic pole is called its pole strength. The inverse square law of magnetism stated that the force of attraction or repulsion between the two magnetic poles is directly proportional to the product of their pole strengths and inversely proportional to the square of the distance between them, and acts along the line joining the poles. Magnetic permeability or mu of a medium is defined as its ability to allow the magnetic lines of force to pass through it or to allow itself to be influenced by the magnetic field. The permeability of free space mu naught is equals to 4 pi into 10 to the power of minus 7 Henry per meter. The ratio of magnetic force in a medium to the magnetic force in free space is defined as relative permeability mu r of the medium. The relation between absolute permeability mu and relative permeability mu r of the medium is mu is equals to mu r into mu naught. The unit magnetic pole is that pole which repels with a force of 10 to the power of minus 7 newtons from an identical pole kept at a distance of 1 meter. Magnetic field induction or magnetic flux density, B, is defined as the magnetic flux passing through a unit normal area.